Hi everyone, welcome to another STEM tutorial. In this video, we'll continue looking at finding the roots of singular nonlinear equations, and we'll do so with the Newton method. So essentially what we'll be doing is we'll be looking at what x gives me f of x equals 0. So again, we have a cubic polynomial with one real root, which we can identify that 0 is approximately located here. In this video, we'll be focusing on the Newton method. So what we've done is we've written down the different steps needed to calculate our root using the Newton method. And we'll be going through them one by one with a simple explanation to help you understand of what's going on our plot here. If you want more detail on the Newton method and how the equations were derived, then please refer to our more detailed Newton method video. So our first step is to guess one x value. So this is again different from the bisection method where we need two. Here in the Newton's case, we only need one x value. So in this example, we'll choose x equals 6, just for the sake of demonstrating what we're doing on the plot. So here we'll choose our x value, x1 equals 6. And then as a next step, we need to calculate our next x value with the following function. So we see our function f of x written here. So what we'll do is we'll write down the equation for our first derivative here. So we know that our f prime of x equals 3x squared minus 2x plus 1. And then, knowing our first derivative, we'll plug in our values in this equation here. So we know that our x1 we've defined as 6. x1 equals 6. Then we'll calculate our f of x1, which equals, again, we're just plugging in our x in this equation up here, equals 6 cubed minus 6 squared plus 6 minus 5. And if you plug these values in your calculator, you'll get an answer of 181. Then, for this equation here, we need to calculate our f prime of x by plugging our x values in this equation. So we'll get f prime x1 equals 3 times 6 to the power of 2 minus 2 times 6 plus 1. And again, if we type this into our calculator, we'll get an answer of 97. So then plugging everything finally into this equation here, we'll get that our x of I plus 1, which equals x2, equals our x1 minus f of x1 over f prime of x1. And so if we substitute in our values, 6 minus 181 over 97, we see that our x2 equals 4.13. Great, so now what we've essentially done is we've chosen our x value here, which is our x1, and by applying this equation, we've essentially drawn a tangent along this curve and looked at where does this tangent intersect with our 0. So here, where does this tangent intersect with our 0 line, f of x equals 0? And so we'll see what we've calculated is this value of 4.13. So here we have x2 equals 4.13. And so what we're going to do as our next step is calculate our f of x plus 1. So we're doing this as well just to see how close are we really to our f of x equals 0. So here we have now our x2 equals 4.13, and we're going to calculate our f of x2 to see whether or not we've met any of our stopping criteria. So again, our stopping criteria tells us when can we stop iterating, when are we close enough to our 0. Okay, so we'll go and move and calculate f of x2 which is again just plugging our values in the equation up here. So 4.13 cubed minus 4.13 squared plus 4.13 minus 5. And if we calculate this in our calculator, we'll get an answer of 52.52. So we'll see that this value of 52 up here is nowhere close to 0, what we're looking for. So we'll have to continue iterating. So we're going to again now calculate our f prime of x so that we get our next x. So I'll just demonstrate this once more. So we have our f prime of x2, which equals 3 times 4.13 squared times 2 times 4.13 plus 1, which equals 43.91. And then substituting this again into our equation, we get x of 3 equals our 4.13 minus 52.52 over 43.91, and then typing it in the calculator, 2.93. So again, this here was calculated with this equation up here. And so if we calculate our f of x3, so we have our x3 equals 2.93. If we again calculate our f of x3, we get an answer of 14.63. So what we've done here is again drawn another tangent that intercepts with our 0. So this is where we have our x3 equals 2.93, and our function value here equals 14.63. But still, if we consider our stopping criteria, this is nowhere near 0. So what we'll have to continue is iterating through this process. What you'll see is we then iterated for x4 and saw that our f of x4 equaled 3.46. So if we compared it to our stopping criteria, this value was not less than 0.5. So we moved on to calculating our x5, and here we saw that our f of x5 equaled 0.48. And this value is indeed less than our 0.5, so our stopping criteria was met. And then we can officially say that our 0 is located at x equals 1.94, with the f of x being quite close to 0. So this wraps up our Newton method tutorial. We hope we could help clarify this method. If you enjoyed this video, then please hit like and subscribe below. If you have any questions, feel free to leave them in the comments section below, and check out our website, stem-tutorials.com, for more exercises. Finally, if you would like to learn more about the Newton method's derivation, or if you would like to view our numerical methods playlist, please check out our corresponding videos. Have a lovely day.